Okay, section 6.2, multiplying and dividing radical expressions. And that's what we're going to do. So there are a couple of properties that they wrote here. If you would like to write them, go for it. You can use it on a quiz, but not on a test. So here's the first one, combining radical expressions. This is for products. Basically, all you probably need to write is products combining radical expressions, and then probably this part right here. It basically just tells you what to do with the numbers underneath the radical when you're multiplying. So if you have two numbers that are nth roots, like third roots or fourth roots or whatever they happen to be, if these numbers are the same, those little numbers on the outside, which were indexes that we learned the other day, if those are the same, you can multiply the parts underneath. If they're not the same, you can't do anything. Okay, so for instance, if one of these was a 2 and the other was a 3, you could not do anything with those. If they're both 3s, then you can multiply the numbers underneath. So we'll do a couple of them so you can kind of see that. Super easy, but just know that you can't combine them unless those ends are the same. So I'm going to put that in here. Indexes must be the same. So those are the two numbers we're looking at. So with the first two, notice how we have the cube root of 6 and the square root of 2. Can we do anything with those? No, because what's the number when there's no number out here? It's a 2. Or you can look at it and go, well, this one has a 3, but this one doesn't have a 3. They're not the same. Okay, so this one we're going to put cannot be simplified. And then I'm going to put indexes not equal. Okay, what about the next one? We have the cube root of -4 and the cube root of 2. Are they both 3s? Yeah, so we can go like this, the cube root of, and it says to multiply the parts underneath. So we're going to take -4 times 2. So when we simplify, we get the cube root of -8. And what is the cube root of -8? Here's where we go back to the lesson we've already learned. So if it's a number, you can type it in your calculator, and you get -2. Now, with an odd exponent, do we only have one answer? Yes. So think about what we did in 6.1. We're still going to be using those. So it is -2. If this were an even root, then we'd have to think, how many answers do we have? We could have 2. We could have none. You know, what is it? So if this were a 4, would you have an answer? No, because we can't do the fourth root of a negative number. Okay, if you did the fourth root of a negative number on your calculator, it would give you that error, and you'd say none or, empty set or something like that. So, pretty easy so far. We're going to do stuff that's a little bit harder. Okay, so if the radicand, that's the number underneath, A, has a perfect nth power among its factors, you can reduce the radical. Make sure you reduce in simplest form. Okay, so if it's a perfect nth root, which is what we're looking for, we do want to reduce it. And I don't know if you really need to write that down. You always just need to simplify as far as you can. So let's simplify a couple that have both numbers and variables. So what's the simplest form of the cube root of 54? So the first thing I would check is, does 54 have a cube root? So type it in. If you get a decimal, then it doesn't. If you get a number, that is it. Okay? So when you're reducing, you do not want to go to decimals, only if it's whole numbers. Like if you had cube root of 64, that's 4. It doesn't have any decimals after it. So this would give you a decimal, correct? Okay, so next thing we're going to do is we're going to do a factor tree. Okay, so 54. I'm going to do 9 times 6. 9 goes down further, 3 times 3. And 6 goes to 2 times 3. Now, if we're looking for a cube root, how many numbers do we need to take one out? You need 3. So this one will come out as a 3. The 2 will not go anywhere. It will stay. So far for the numbers, we have 3, and then we have cube root of 2. Now we're going to kind of work on the letters. You can do it a couple different ways. The book usually does, for instance, numbers to exponents, but you can do it a different way. So how many x to the 3's can we take out of an x to the 5? Okay, and if you're kind of wondering what I mean, okay, if we have x to the 5, that means we have this, right? Now, these could come out, right, because we have a set of 3. So that comes out as an x. And then how many are left? 2. That stays in. So this would be 3x on the outside, cube root, 2x on the inside. So if it's hard to think of like the exponent to an exponent like they do, it's just like writing it out as 5, and then you're taking out however many you need. So if it was a 4th root, we would circle 4 of them, and 1 would come out. Okay, so that's kind of what you're thinking here. Oh, and I should have written squared there, okay, because there was 2 left. So don't write 2xx on the inside, write 2x squared. Yes. Okay, and the 3 is the cube root, not 2x or 3x cubed. Okay, so if you have a tiny little number there, I'm going to know that it probably, maybe I should put it, I'll tuck it in a little bit tighter here. So 3x cube root, 2x squared. When the exponents are odd, we don't have to worry about absolute value or anything, right? Because it is what it is. Okay, let's do this one. We have the square root of 72x cubed y squared times 10, or square root of 10xy cubed. Square root of 10 is not a thing. How about square root of 72? That's not a thing either. So what you can do is you could multiply them and make it 720, but that's a pretty big number, right? So I'm going to do them separately like they are right now, and then we'll just combine the numbers at the bottom. So I'm going to work on the numbers. And then how many do we need to take it out when we're dealing with square roots? 2. So we need pairs. Okay, so if you want to put the 2 out here to indicate how many you need, go for it. So I'm going to do a factor tree of 72. So 8 times 9, 3 times 3. So there's one pair. 8 would be 4 times 2 and 2 times 2. Here's another pair. I'm going to circle them as we go. The one that I have left is right here. I have a 2. Now, what about a 10? Okay, when I do a 10, I get 2 times 5, right? But when we're putting them together, wouldn't all of these leftover numbers be together too? Like these and this, wouldn't that still be left? Because we're really kind of multiplying them. So can I take anything else out? 2 times 5 times 2? We can take another 2 out, correct? Because there's 2 of them. It doesn't matter that it's a 10 and a 72 because we're really multiplying them anyway. So if you wanted to, you could take all of the bottom list of all these numbers, and I'm going to do it this way instead. I'll show you. Let's go like this. So 72 was 2 times 2 times 2 times 3 times 3, and 10 was 2 times 5. So I'm doing just the whole bottom list all together. Now I'm going to circle pairs of 2. Okay, so here's one. I already did it, but here's another pair. And then here's another pair. Those 2 go together. So you're circling all the pairs of 2 in the combination of the 2 numbers together. So we have 2 on the outside, another 2 on the outside, another 3 on the outside. What do we do with all of those? Yep, we're going to multiply them. I'll do that in a second. 2 times 2 times 3. And then it's going to be square root. We still have a 5 left. And I haven't done anything with the variables yet. Okay. Now, when we multiply an x cubed times an x, what do we do with those exponents? So if I was trying to put these two together, what would it be? X to the 4. Or you can think of it this way. If you list them out, you have 3 x's on the first one, 1 x on the second one. If you add them all together, you'd have 4. Or if you look at how many x's you'd have a 4. So my x is to the 4, and my y would be how much? 5. So add exponents. I'm going to go like this, add exponents. Okay. Now I'm going to multiply the numbers, so 4 times 3, you'd have a 12 out there. So the 5 is actually done, but now I need to take out pairs of 2 for the x's. So here's what I'm thinking in my head, and I probably wouldn't write anything, but here's my x's. Here's my y's. How many pairs can I take out of each? So here's a pair, here's a pair. What would that come out as? X squared. So you have 12 x squared. We have another pair of 2 and another pair of 2. That would come out as a y squared. How much would I have left? Y. So it would be like the square root of 5y. Okay, so I'll go like this and like that. And you don't have to write those out. If you're like, okay, if I have 4 and I'm taking pairs of 2 out, that would be 2. 4 divided by 2 is 2. You can do all that in your head. I'm just kind of being very specific about what I'm thinking. Now, here's the thing. We have an even root, don't we, or an even index. So we have to think, do we need absolute value on this one or do we not? When you have something squared sitting out here on the outside, is it going to matter if it's an even number or an odd number or positive or negative number when I put it in there? No, because I could put a 2 in there for my x, right? It would be a 4. If I put a negative 2 in there, wouldn't it still be a 4? So if there's no question about whether it's going to be positive or negative, then you don't have to deal with the absolute value. So here, since they're both squared, I would not have to do anything, and this is my answer. What if I had an x squared, but I had a single y? Then would it matter? Yeah, because if I put a negative 1 in for y, it's going to stay negative. But if I put a positive number in there, it's going to turn positive. We want to keep it whatever it is. So here, if I did have just a 1, it would be 12x squared, absolute value around just the y part, and then whatever's underneath. And it's only those numbers that you're taking out. The ones that are left, you don't have to deal with. Okay. Here's another little property. This is for quotients. So again, you probably need that. We're going to have real numbers. Basically, b can't be 0 because you can't divide by 0. And basically, we have seen this before. If you have the nth root of a number and an nth root of another number on the bottom, as long as these numbers are the same, you can combine them together and simplify it as a fraction. Or if you get a fraction and you don't know how to simplify, you can separate them and do them separately. You can go either way. So we're going to be doing the same thing we just did, only you have to do it twice because there's one on the top, one on the bottom. Did everybody have that? Okay. I'll keep it there for a second more. Okay, we good? All right, so let's do these two. So these are separate right now. What I'm going to do is I'm going to put them together. So I'm going to take my two separate ones. They're both square roots. So I'm going to put them together like this. 18x to the 5 divided by 2x to the 3. Now, can I put 18 divided by 2 together? Now you can, which is 9. So I have a 9. And when you have something like this, what do you do with those exponents? Subtract. So if we went like this, x times x squared would be x to the 3. When you multiply numbers with the same base, you add their exponents. When you divide numbers, I'm going to say subtract over here. You subtract their exponents, so you get square root of, I'm going to make this a little bit different. So you get a 9x to the 2. So now we are done with the fractional part. Now we need to simplify the rest. What's the square root of 9? 3. What's the square root of x squared? X. Because remember, when you take two x's, you're looking for pairs when that outside number is a 2, and 3x is your answer. Okay, let's do another one. So we're going to put this one together, just like we did the last one. So it's going to be the cube root of 162y to the 5 over 3y to the 2. Because right away, I don't know the cube root of 3, I don't know the cube root of 162, so you can't really do them separately. So we're going to divide 162 divided by 3, and you get 54. And then what do I do with my exponents again when I put these together? Subtract. So I'm going to just write that equals y to the 5 minus 2. So you get a y cubed. Can I take the y all the way out? Yeah, so basically when you get to this far, if this number matches that number, you can take it out. So I already know that I have a y sitting on the outside. And didn't we just do 54 just a couple minutes ago? We factored 54, didn't we? And it was 3 square root 6. Is that right? 54. Oh, we need 3. Okay, let's do it again. I'll do it in a different color so it stands out a little bit. Okay, we did square roots then, I think. 54 was 9 times 6, 3 times 3, 3 times 2. So what can I take out of there? A 3, because we need 3 of them because it's a cube root. So there is now a 3 on the outside. And a y on the outside. And what's left? And here it is what it is. So it's odd, so we can just let it be. Now, do you guys remember when you did square roots and things in Algebra 1 and you couldn't leave the square roots on the bottom? That's called rationalizing the denominator. So when they ask you to simplify all the way, that's what they're going to do. So these examples that we did, there didn't end up to be anything on the bottom, but what if there is? Then what do you do? So rationalizing just means we're going to rewrite the expression so there's no radicals in any denominator and no denominator in any radical. Okay, so this is the hardest one right here. And it's only because it's not just going to be square roots anymore. It could be 3, it could be 4, it could be 5. How do you do those when it's not just a square root? So the first thing we're going to do again is separate them. So it kind of looks like this. Or no, we want them together. I was thinking that it was the way it was. Can we take anything out like it is? We don't know the cube root of 5, right? We don't know the cube root of 12. Nothing really looks like it can do anything separately. So that's kind of what you want to do. So if you can't do that, we are going to separate them this time. So we have 5x squared, cube root of that, over the cube root of 12y squared z. I should have just written it over here. Okay, so just a little backtracking here. When we had square roots, like 7 over the square root of 2, how many did we need to make the 2 come out? We need 2, right, when it's a square root? So back then, all we did was, oh, I have to multiply the top and the bottom times the same number. So I usually would get then 7 square root 2 over 2, because the square root of 2 times the square root of 2 is 2, which remember is square root of 4, which simplifies to 2. That's what we're trying to do. But back then we only worked with 2's. What do we do now with it of 3? We can't just take this times the cube root of 12y squared, z again, because there's not 3 of them. Okay, so here's the trick on this one. You want to make sure that whatever you multiply by, it simplifies everything so you can take it out. Okay, for instance, on the y, I've got 2 of them. How many y's would I need to take it out? I would need 1 more to make it 3, okay, because it needs to match that outside number. How many z's would I need to make 3? 2. So it's going to be different like every time you do these, because you have to make them add up to the number on the outside. Okay, so here's what I'm going to multiply by this time. And it's going to be the top and the bottom. Whatever I multiplies by is going to be the same on the top and the bottom, but it's not going to be the same as the bottom part. When you do the 12, we're going to deal with a number here in just a minute. I'm just doing the letters for now. So I need a y and I need a z squared. Okay, and when I do that, it's going to be y to the 2 times y, which would be y to the 3, z times z squared, which would be z to the 3. Okay, and you need to do the same thing on the top. Now, when you do the numbers, you can do kind of the same thing. If I do the factor tree of 12, I get 4 times 3, and then 2 times 2 times 3 at the bottom. Keep that in mind. So how many more 2's would I need in order to take the 2 out? 1, so I'm going to put a 2 here. How many 3's would I need? 2. Okay? And you keep it the same on the top. Now you multiply straight across. Okay? So when we do that, I'm just going to list what we have and then we'll simplify. You'll get better at it so you won't have to list it out, but here's kind of what I'm thinking. So it's cube root on the top. Okay, so cube root of, we have a 2 times a 3 squared times a 5. I'm just kind of gathering my numbers together. And I have an x squared and a y and a z squared. On the bottom, I'm going to have now this we rewrote as 2 squared times 3. 2 squared times 2 times 3 times 3 squared. So I'm gathering my 2's, putting them together. I'm gathering my 3's. I'm going to put my y's together and my z's together. Now, if I were doing this, I would lump them all together right now. So you're going to be going, oh, I need to put my y's together. I have 2 here and I have 1 there. I get 3. You can do that, but I'm just kind of spelling it out, especially for those that aren't here. Now we're going to do a little bit of simplifying. In the numerator, can I do anything with that except for multiply my numbers out? I don't have any more x's. I don't have any more y's. I don't have any more z's. Those stay the same. So I'm going to multiply 2 times 9 times 5 because 3 squared is 9. So 2 times 9 times 5 would be 90. And x squared, y, z squared. In the denominator, can I take this 2 out now? I've got 3 of them. Now I can take it out. So I'm going to pair this up and it comes out as a 2. Can I take my 3 out? Yep, there's 3 of those. Can I take my y out? There's 3 of those. Can I take my z out? There's 3 of those. Okay, that's what you want because we want to get rid of that whole radical, whatever number it happens to be, we want to get rid of it. So here, the only thing I would need to do is make that 2 times 3 a 6. So it's going to be a 6yz on the bottom, and the top part we're going to leave like it is. Now, you might be thinking, do I have to simplify that 90? We kind of already had that simplified, didn't we? It was 2 times 3 squared times 5. Those are all prime numbers, so you wouldn't have to do it again. If it was a square root, then we could, but it's a cube root, so we can't. Still looks really ugly, but you can't do anything with it. Yep?
How did you get the 90? How did you count of it?
The 90? Okay, I did 2 times 3 squared times 5. Because you can't take anything out, because there isn't a thing of 3. Most of the time, the top part will still look pretty ugly. The bottom part is what will look way nicer. Okay? Here, there was 3 2's, so I took one out. There was 3 3's, so I took that out. There's 3 y's and 3 z's, so I can take everything out, and that's what you want. If you have something stuck on the inside, you didn't multiply by the right thing. Maybe you left one out, or you didn't count them right, or something like that. Okay, so if there was a 4 out there, we would have had to make all of these have 4 things in them in order for it to cancel, or 5 things if there was a 5. I don't know how ugly these get in your assignment, but just so you know, whatever the exponent on the outside is, that's how many you need in order to take it out. So that's what these are going to kind of look like. Okay, so let's do 2 just for practice. And you guys can just put these on your assignment. We'll go through them just so that everybody kind of goes, oh, yep, I get that. So try this one. What is the simplest form? And then we'll go through the answer here in a minute.
So when we do the variables, like when we list them all out, can we combine all the x's together and all the y's together?
Yep, that's what I do. So you don't have to do like 5 and then in one separate, put them all together. Okay, so are you guys getting what I have gotten up here?
Yep.
Okay, so at the end, now we just have to think about this. When there's a 2 on the outside, is that even or odd? Even. When I plug numbers into the outside of this thing, if I plug a positive number into x cubed, it's going to stay positive. But if I put a negative in there, what's it going to do? Change it to negative. So what do we need to do on this one? And we need it on both of them, right? So we want numbers that we're going to plug in there to get exactly what we have. So I'm putting in an absolute value here, around the x cubed, y cubed. Generally, some books will say whenever it's a square root, it's the principal square root that you want, but just so that you know kind of how that works, I'd rather that you do it on all of them. And remember the inside stuff, it doesn't matter. We're going to do one more, and this is a division one. So what do we do here? So cube root of 7x divided by the cube root of 5y squared.